Okay, so first of all, welcome all of you to this seventh episode of the second season of the O-MESS. Today we have two talks, as always. By the first one will be by Leesa Fleury from the University of British Columbia, and the second one by Vitaly Neustroyev from the University of Oulu in Finland. And the talks, as always, will be 20 minutes plus 5 minutes of questions, and then we will have 30 minutes of a coffee break, a virtual coffee break. So if everything is okay, Leesa, we can start with your first talk, I think. So Leesa Fleury will talk about the cooling of massive white dwarf from the Gaia data release 3. So do you want to start?
Yeah. So I just wanted to start by thanking the organizers of O-MESS for doing such a great job organizing this seminar series and for giving me the opportunity to give this talk. So my name is Leesa Fleury. I'm a PhD student at the University of British Columbia, and I'm going to be talking about the cooling of massive white dwarfs from Gaia Early Data Release 3. This is work that I did in collaboration with Ilaria Caeso and Jeremy Heil. And everything that I'm going to present today is available on the archive at this archive ID. So just to give a brief overview of what I'm going to cover, I'm going to start by giving some background about the Q branch, and in particular the anomalous cooling delay that's been talked about for white dwarfs on the Q branch. I'm going to spend a lot of time talking about the cooling age distributions for massive white dwarfs in Gaia EDR3, and finish with a discussion of implications for merger products among the most massive of these white dwarfs. So all of the data that I'm using in this work comes from the Gentile Fusillo et al. 2021 catalog of Gaia EDR3 white dwarfs. I've selected a sample that's within 200 parsecs of the sun and have been identified as white dwarfs with at least 90% probability, as stated in that catalog. So here I'm showing the color magnitude diagram for the Gaia EDR3 white dwarfs. And I want to draw your attention in particular to this cluster of stars that forms a horizontal or nearly horizontal trend. Not sure, can you see my cursor? This is a quick question.
Yes, we do.
Yeah, okay, great. So this cluster of stars here that has been zoomed in on in this second plot is referred to as the Q branch. So this was a feature that was first revealed in Gaia DR2. And it's largely attributed to white dwarf crystallization, even in standard cooling models, and specifically when white dwarfs undergo a phase transition from the liquid to solid state, the release of latent heat from that process slows down the rate of cooling and leads to a pileup of stars, or that you would expect to look similar to what we see on the Q branch. So here I've just overlaid contours of constant mass as this green series and constant age as this purple series. And so a white dwarf of a given mass would follow a cooling track, typically along one of these green contours. And I've also overlaid on these plots thresholds for critical features in cooling. So the dashed lines indicate for an oxygen neon core white dwarf, the thresholds at which 20% of the core is frozen. It's the top line, 80% of the core is frozen, it's the bottom line. And the solid lines similarly denote thresholds of 20% up top and 80% frozen for carbon oxygen white dwarfs. So we see the pileup of stars solidly in the regime of white dwarf cooling. So some of this feature was expected. There is an expected cooling delay due to white dwarf crystallization. However, in Gaia DR2, it was noted there was an excess of stars on the Q branch above what you would expect just from standard crystallization. And this has challenged our understanding of white dwarf crystallization in the last few years, especially as pertains to neon 22 sedimentation. So with the really recent release of this Gentile Fusillo catalog for Gaia EDR3, I thought it worthwhile to revisit this cooling anomaly problem, look at the distribution of cooling ages in particular for these massive white dwarfs in the newest data release. So to construct these cooling age distributions, we rely on white dwarf cooling models to convert the photometry, the color and magnitude measurements of the white dwarfs to masses and cooling ages predicted by those models. So I've considered a variety of different models. These are all publicly available here through this package provided by Zihao Chung. So I have kind of two key sets of models I've looked at, the Montreal models, which are carbon oxygen core models at all mass. I've considered, in the case of hydrogen envelope white dwarfs, both thick and thin hydrogen envelope models. And the La Plata group of models, as I've termed them, because it combines models over different regimes, all coming from largely this group in La Plata. And these have oxygen neon cores for masses above 1.1 solar mass and carbon oxygen cores at lower masses. And so and another key consideration in constructing the distribution of cooling ages is to ensure that our sample is complete. And so I do this by constructing reduced sampling volumes for the faintest stars. The incompleteness manifests in the plot I've shown here. Here V is the volume, V max is the volume of a sphere of radius of 200 parsecs from which the initial sample was drawn. And so incompleteness in this curve manifests as downward curvature, deviation from a straight line. So I draw these limiting volumes in which the sample of white dwarfs at a given magnitude will be complete, and only keep white dwarfs within that limiting volume. And then in constructing the cooling distributions, I correct for this reduced sampling volume by assigning a weighting that just corrects, gives the expected number of white dwarfs you would see if we could actually see out to the same volume at all magnitudes. So after doing all of that, the first thing I look at is the joint distribution of masses and cooling ages according to the different models. That's this top row of plots here. Overlaid on this plot, I've shown the freezing lines that were also shown earlier in the CMD being converted to mass cooling age space. And so from bottom to top, these are the lines of 20% oxygen neon frozen, 20% carbon oxygen frozen, 80% oxygen neon frozen, and 80% carbon oxygen frozen. These horizontal lines here just indicate where I'm later going to divide up the sample into mass bins. So it's not important for highlighting features of this particular plot, it's just for a point of reference for things I'll show later. And so the striking feature to me about this plot is the pile-up, notable increase in density that we see in all of these models, starting during the regime of core crystallization, but extending well beyond it. And so this pileup is not something that could be explained just by modifying particular oxygen neon crystallization, because we're still seeing the pileup after nearly the end of carbon oxygen crystallization, which occurs already after when oxygen neon crystallization certainly needs to finish. Now, this dramatic increase in density also coincides with when a burst of star formation was found to have happened in the galactic, in the history of our solar neighborhood. So in this bottom plot here, I've essentially marginalized over mass. So these are white dwarfs in the mass range of 0.95 to 1.25 solar mass. The different colors just indicate the atmosphere that the white dwarfs are being classified as having. So what we're interested in here is the summation of all of these. And in these plots, I've also shown the star formation rate that was determined from Gaia DR2 main sequence stars. This is from Moore et al. 2012. And these star formation rates are normalized in each plot to the total number of white dwarfs with a cooling age younger than or equal to 3 gigayears for reference. And so this is exactly what we would expect if white dwarfs are predominantly produced through single stellar evolution. For white dwarfs of this mass range, their pre-white dwarf lifespan is negligible compared to the cooling ages that we see here. It's less than 100 million years or so, and we're looking at cooling ages on the span of gigayears. So we would expect white dwarfs of this mass, and specifically the cooling age distribution of these white dwarfs, to be a direct tracer of the star formation rate, which is what seems to be happening in these plots. But to avoid binning error and to do a more vigorous statistical analysis of this, I looked at the cumulative distributions. And in looking at the cumulative distributions, I've also looked at 3 equally spaced mass bins within the sample that I showed on the previous slide. And so here in blue, I show the empirical distributions, both in the cases of applying the weighting and not weighting the distribution. In orange, I show the star formation rate. And for reference, I also show a uniform distribution as a dotted black line. And we see for the 2 lightest mass bands, which are these top 2 rows, both visually and statistically when run the analysis, statistical consistency between the empirical distributions and the star formation rates for most of the models considered. But interestingly, for this heaviest mass spin, the empirical distribution is much closer to uniform. It doesn't actually trace the star formation rate. So this we take to be an indication that there might be merger products among these white dwarfs, a substantial number of them, because specifically a white dwarf that's produced through a double white dwarf merger will appear younger using cooling ages determined in the method you just described, compared to a white dwarf with the same mass that was just directly formed. Essentially, the white dwarf's lifetime just gets reset after the merger, but the two white dwarfs that created the merger product had already lived to some older cooling age before that formation process. So to determine a prediction for what the cooling age distribution should be for these merger products, we need to know, okay, thank you. We need to know the distribution of the delay time, and then you need to convolve that with the star formation rate to get our prediction. So I use the delay time distribution from Chung et al. 2020. These come from binary population synthesis results and are available for a mass spin very similar to what I'm interested in, and convolve that with the star formation rate. And that produces this black line that's again normalized to 3 gigayears. In this plot, I show the empirical distributions according to the best fit models from the previous analysis for the different masses. And these dashed lines of the same color are just the star formation rate normalized to 3 gigayear point. And so we see the effect of merger products to kind of push this peak from star formation burst to earlier cooling times. And so I then model the distribution for this heaviest mass spin as a linear combination of the merger product and direct evolution distributions, and fits for that. And the result is this red curve. It's the combination model that gives a good fit to the data. And here in gray, I show the fraction of merger products among white dwarfs of a given cooling age. And we see that merger products are more common among white dwarfs that are forming more recently. From the fits, 80% of white dwarfs forming today are merger products, and about 50% that have formed over the last 4 gigayears are merger products. And these fits are in particular for the Montreal thick models. So to summarize what covered so far is from the Gaia EDR3 photometric cooling ages, we don't see substantial evidence of anomalous cooling delay anymore after counting for the star formation rate as measured from main sequence stars. The cooling age distributions for the two lightest mass spins considered are statistically consistent with the star formation rate. And for the heaviest white dwarfs, we get a good fit as long as there's a large fraction of merger products. Now, the fact that the carbon oxygen core models gave the best fit might bother some people, because it is thought that oxygen neon core models are more accurate in this case, but there has been work in the literature showing how carbon oxygen core model or white dwarfs in this mass range can be produced. So I think just more work is needed to understand what's going on there. And so I'll just leave you with the references that I've cited throughout this talk. And the reference listed here under Fleury is where you can find more details about this work if you'd like to go looking yourself. And I'm here to answer any questions if you have them.
Okay, thank you very much for this very interesting work, by the way. Let's see, do we have questions here? Is there anyone who wants to make a question? Oh, now it's time.
Can I have a question? Sorry.
Sorry?
Can I have a question?
Yeah, please go on.
Yeah. So thank you for this interesting work. So yeah, I think it's very interesting, but there's one caveat I want to mention, which is about kind of now we have you're analyzing the number distribution of the white dwarfs, right? So first I have a question of how did you deal with, maybe I missed the beginning part, but how did you deal with the effect of the thickness of the disk, right? Because the younger stars will also have a thinner, are distributed closer to the disk, and then because of the selection effect, the guy can only see kind of a volume, and for the younger stars you'll see most of them, but for the older stars basically the disk is thicker, so then there's a selection effect that we cannot see all the white dwarfs within the column, right, of the disk, but only a fraction of them. So I wonder, did you have any kind of correction for this? And also another question is about the velocity. So kind of in some of our works, so we look at the velocity. Kind of one of the reasons is because of these selection effects hard to correct. So I wonder, have you tried to also combine the velocity information or not? Thank you.
So for the velocities, I'll field that first. I'm in the process of looking into that. So it is something that's on my radar for sure. I just don't have the results for that yet. So yeah, I haven't talked about that here. In terms of for correcting for the disk, the only correction I've done so far is this procedure I described with the reduced sampling volume to account for the completeness, but that hasn't yet been treated as a function of, distance from the disk. That's something I'm working on doing in looking at the velocity distributions.
I see. Thank you. Yeah, just for comment. I mean,
yeah.
So I agree with your conclusion. But the first you said there's no cooling anomaly. I think if you combine the velocity information, maybe still we have to say there's a cooling anomaly.
Yeah, it may have been a strong statement. I think there is kind of reduced evidence, at the very least. But I am certainly aware that velocities are still something I need to look into. And I know in your work you point out particular the discrepancy between dynamical and photometric ages, and that's a big feature in looking at this cooling anomaly. So,
okay. Yeah. So do we have more questions? Yes. Don't be shy.
Yeah. So I have a couple questions. My main question was sort of along the lines of the second thing that Sihao asked about the, just the kinematic age indicator. Sounds like you're still looking into that. I guess my comment would be that, if you're basing the analysis on number density alone, it seems both consistent to say that, there maybe is no signal of a cooling delay in that data there, but it's not necessarily the same thing as saying there can't be a cooling delay, right? Like your data could still be consistent. I think. I'm interested to get your take on that.
Well, yeah, I mean, with this analysis, you can't necessarily rule out the possibility of a cooling delay. You can just state that the results that I see are kind of statistically consistent with themselves. So it doesn't firmly rule out the possibility there being any anomaly. I just don't see any particular evidence of it in what I've looked at so far.
Thanks. Okay, I think I'm tracking.
Okay.
Thanks.
Now we have another question by Maria Camisasa. You want to?
Hi, thank you, Leesa, for your talk. I'm Maria Camisasa. I wanted to ask you, like, you find a very good agreement with the merger models, like you say that there's a high percentage of merger models, right? Yes. So what do you consider for that, like carbon oxygen or oxygen neon, or what is the metallicity the neon 22 abundance that you're considering?
So what I showed in the talk was just this case of the thick hydrogen Montreal model carbon oxygen core white dwarfs, which were the best fit results. In the paper that the updated version should be on the archive now today, I looked at all three sets of models that I discussed. So I have a fit for the oxygen neon white dwarf models as well. The predicted, or the fraction of mergers indicated by those fits is lower by at least 10% in that case, oxygen neon models. I just didn't have time to get into the details of all the different models I considered in this talk.
But those models are carbon oxygen core, right? I mean, in the ones that you find best fit and the ones that you consider for the merger? Yes. Okay.
Yeah, the ones that actually give kind of a good fit are the carbon oxygen core models. The oxygen neon core models don't give a great fit. There's definitely,
we all have
there. That's why I wanted to cite, the results here that
I think that you can then discuss this during the coffee break. So because now we need to move to the next talk.